and dynamics of a frustrated magnet. Thank you.
Okay, thank you very much. And I'd like to start by thanking the organizers for the chance to give this talk here. It's very nice to be here and what promises to be a really nice conference. Okay, so I want to tell you about two different things. A bit about topological transitions at the beginning, and then discuss a bit about the dynamics. We'll see that when I want to talk about the topological transitions, we'll run into problems because of the dynamics, and then we'll go a bit further into the dynamics and see why those problems arose and why they're interesting on themselves. So this is mostly an experimental talk. There's a little bit of theory we've done, but it's mostly experimental. And this was done in collaboration with many people, in particular Rodolfo, Demian, Mauricio, and Lucas from Argentina, Roderick and Attila from Dresden, Alan Tennant from Tennessee, Mariano from UBA in Buenos Aires in Argentina, Ludovic and Peter from Bordeaux and Lyon, and then Alex, Mark, Fabian, Cliff, and Andy, also from Dresden in Germany. Okay, so let me start with the first bit, topological metamagnetism. So we all know metamagnetism. We know this from our undergraduate years. We know it's mostly seen in antiferromagnets, and it's either comes through a second order phase transition or first order phase transition. We know it's always, or many times it's talk about how it's similar to the gas-liquid transition. We see it in antiferromagnets. We see it also in itinerant ferromagnets. We did a bit of work on itinerant ferromagnets at one point on the metamagnetism of that. But the question driving this work was whether one can see metamagnetism of spin liquid. So let me start by the system we're going to consider. We're going to consider a pyrochlore lattice. So this is a lattice made of tetrahedra. They're all connected by the corners. And these are Ising spins sitting there. And we're going to consider two systems. The first one is the spin ice, which can be described by this very simple Hamiltonian. And the other, it's a monopole liquid, which is described by that very simple Hamiltonian too. Right. So let's start with spin ice. So when you look at this tetrahedra, the first question you ask is, well, okay, what's the ground state of these? If I have this Hamiltonian, and okay, this is a pairwise interaction, so we look at pairs. We see that these are all the pairs we can get, and we see that if we look at the components, we see that a ferromagnetic interaction would favor these states, while an antiferromagnetic interaction would favor those. So essentially, it's sort of counterintuitive in the sense that the ferromagnet is the one that frustrates the system. You see that there's no proper order coming here. There's order coming in the case of antiferromagnetism. So in the case of ferromagnetism, you get these 6 possible states for a single tetrahedron with just 2 spins pointing in, 2 spins pointing out. Then you wonder, okay, now when I construct the pyrochlore lattice, what do I get? Do I still get a very degenerate state? What's the residual entropy I get, if any? Okay, so essentially, yes, you do get residual entropy. The idea is you have 2 spins per tetrahedra, and then you have 6 possible choices. These are the 6 possible states I showed you, but there's a 1/4 chance of matching these, right? So you have 1/2 chance for each of these spins to match, and that gives you the 1/4 chance of matching. So when you look at the residual entropy you get, you're essentially getting ice entropy. So this is the same that Pauline's entropy, and that's why people call this spin ice. So there's another way of calculating this, and this dates back to Onsager. And what Onsager said, okay, I can also calculate this residual entropy if I think of now taking one string and threading all tetrahedra, going through all possible ways, just in where spin is pointing in, out where spin is pointing out. And when you do that calculation, you get exactly same entropy. And this is very interesting because this is already pointing out to the fact that you are working on a system whose ground state is a divergence-free state. Right, so the way to think, and I'm going to recur on this many times, that's why I'm spending a bit of time here. The way to think of this is, okay, so 2 in, 2 out means that the sum is 0, and if I go now into a continuum limit, essentially what I'm saying is that I have a divergence that is 0, so my ground state is a 0 divergence state. my excitations are going to be violations of that. It's essentially what I have is an immersion gauge structure. What I'm going to have is charges that correspond to these excitations. So the good thing about this is that I can, at some points, I can forget about the spins, which are many, and I can only think about the excitations, which are few, and construct effective theories out of these excitations, and try to understand the system in terms of the excitations, trying to have to think of the whole spin system. Right, so essentially what I have is this. I have the ground states, which are these neutral states, and then I can either have single charges or double charges. I have 8 possibilities of the single charges, and I have 2 possibilities of the double charges. So you can see that the antiferromagnet, which was pointing all in or out, is favoring the double charges, and that's why it's not giving you a frustration. Okay, and now if you look at how these charges interact, you'll see that they interact according to magnetic Coulomb law, and that's why people like to call these monopoles. Okay, so what about the motivation, this topological metamagnetism? These start with some work that Ludovic, John Joker, Peter, and Roderick did some time ago. That is, what happens if I now put a field that polarizes? So of all these possible states, I choose just one. Essentially put a field along 100, and allow me to project this. It's not so easy to think in 3D. It's easier to think in 2D. Let me to project this, and now I put a field in this direction, and you see that the field polarizes everything, but it doesn't violate this rule, right? So these are still, so each of these brown squares are my tetrahedra, and you see that still have 2 in, 2 out. So the question one can ask is, suppose my temperature is low enough that I can't add any single split effectation. So if I want to do that, that's forbidden, because it costs me essentially 4J to do that, and that's too much. KT is much smaller than J. So is there any other excitation I can get into the system? The answer is yes. I get these topological excitations. Essentially what I can do is I can flip a whole row of spins, right? So from beginning to end of the sample, I flip a whole row. And essentially what you see is that I'm still conserving, let me if you can see this, okay. I'm still conserving this rule, but I now have an excitation that once I put it in, I can move it, right? So it costs me energy, because essentially what I'm doing is I'm paying Z energy because I'm flipping spins down, but I can still move it around, right? So in 3D, it will look like some sort of random walk along the lattice. Right, so let's do a bit of stat-mech on this. So each time I flip a spin, I pay that energy, but each time I move one spin, I can choose 2 possible sites to move. So I have an entropy that goes like k log 2. So if I look at the free energy of that, it goes like this, and that means that I have a critical field or a critical temperature, whatever you want to look at, above which I would have no lines, below which I would have these lines. So essentially what this is telling me is I have this phase diagram. There are no lines here, there are lines there. And essentially I have absolutely no entropy above and have these strings that appear spontaneously below. This is an unusual state in the sense that what we're saying is that there's absolutely no excitations on that side of the diagram. Right, so what are the observables of this? Well, I was talking from the very beginning of metamagnetism, so we expect to see a jump in the magnetization. This is what it looks like. Right, so as I said, these lines are essentially putting a negative magnetization in. So once you start putting lines, your magnetization goes down quite abruptly. And there are no lines there. So the system is saturated. Now, when I look at the susceptibility, it's quite unusual, because there's absolutely no susceptibility on the high field side. There are no excitations allowed there, and there's this divergent susceptibility below. So essentially, once I put one line, I can put many lines in, and this is similar to what people know about vortices in high temperature, or in superconductivity. Okay, so this will be very nice, but once we move to the real world, as you'll see, because of this dynamical constraint, we have the fact that the system freezes at very low temperatures. We need to work at the temperature which is not that low. And essentially, the question we need to ask is, how does this picture modify if some of these poly-like excitations are allowed? Essentially, that means that this is all rounded up, right? Instead of having no lines, you get some. Now, because you have these point defects, you can have like shorter lines. Instead of infinite lines, you have shorter lines. So you have some excitations above, but many excitations below. Right. Okay. So, sorry, I didn't say it. Let me go back. One thing to say is that here, contrary to what we know, is that the critical field here, there's no contribution from the exchange constant. So the exchange doesn't enter into this, and that's something unusual if one for a metamagnetic transition. Right, so the experiment was done on these two different materials. This is the dysprosium titanate and holmium titanate. So essentially, they are very nice spinized systems. So they live on a pyrochlore lattice. They are below 300 K. The moments behave like Ising type spins. They have large magnetic moments. We'll see that that's also relevant. So 10 Bohr magnetons. And the exchange constants are very different. So for holmium, for dysprosium titanate is of the order of 1K. For holmium titanate is of the order of 1.8 K. Okay, so we grew these using these floating zone crystals. So we know that they have absolutely no defects, and we measure them in different ways using a squid, and then we also did some AC susceptibility measurements. I don't want to go into the details of that. I don't think it's relevant. Okay, so this is how the magnetization looks like. So magnetization is a function of field, and we get this sort of metamagnetic transition. This is compared to what you would expect to see in a paramagnet. And once you look at the susceptibility, you see that the susceptibility is indeed this sort of very asymmetric susceptibility, where you have a very high susceptibility in the low field side and a much lower susceptibility on the high field side. Right, so this is for dysprosium titanate. And now if you move to holmium titanate, you have something very similar. The advantage here is that holmium titanate has a higher, it's almost twice J, so that means that at the same temperatures, the number of point defects is smaller, so you get sharper features here. And now if you compare the susceptibility you measure here with the susceptibility you calculate using doing a Husimetry calculation for the ideal Castellani transition. So here there's absolutely no point-like defects, but you see that the general shape, once you add this additional excitation there, is very good. And the other thing you can do is you can measure AC susceptibility. And here, essentially, what you're doing is you're checking how big your excitations are. So look at this. This is 17 hertz, so it's a very, it's almost at the lowest end of what we can measure in terms of frequency. And you see that the peaks here are essentially not there. But when you look at the out-of-phase component, you see these big peaks in the out-of-phase component. And this is telling you that what you're trying to move are big objects. So even at low frequencies, it's very difficult to move them, but they give you a lag in your signal that you see very well in the imaginary part of the AC susceptibility. Okay, so now if you take both holmium and dysprosium, you look at where the transition is, and you can construct this sort of phase diagram, and you see that both holmium and dysprosium, despite one have almost twice J than the other, they give you essentially a single transition. If you compare that with what you expect to find for the Castellani transition, you see that you are near, but not necessarily there. But the thing is that, as I said before, the magnetic moments in both holmium and dysprosium are of the order of 10 Bohr magnetons, so there's a big dipolar interaction between them. So once you put these lines in, these lines see each other, and essentially they repel each other. That means that you need to take that into account. You don't get them starting from zero field. That pushes the field a little bit higher. So if you do a Monte Carlo simulation of what you expect to see once you put these dipolar interactions, you see that the transition sits there, right? Okay, so sorry, that's for the first topological transition. Now I'm going to talk about this other transition, and this is the part of the talk where I go further away from experiments. So this is, as I said, this is the monopole liquid, these 4 spin state, sorry, so 4 spin Hamiltonian. Okay, so you can see that these 4 spin Hamiltonian, these are the pseudo spins, are going to favor just 3 of one kind and 1 of the other kind, right? 3 positives, 1 negative, 3 negatives, 1 positive. So essentially what you're doing is you're choosing, of all those states you had, now you're choosing the single charges one. So instead of having 6 possibilities in the ground state, now you have 8 possibilities. So your residual entropy is now, instead of 6 over 2, it's going to be 8 over 2. And what you get for your ground state is, again, a nice paramagnet. but now it's one paramagnet where you have one charge in each. So you have all possible combinations, and it's usually we have charges of both sides. Right? Okay, so the question is, how do I get a metamagnet out of that? And essentially what I need to do is I need to put a field down in a different direction. Right, so now I'm putting a field along 111. So you see that if I put a field along 111, I can polarize the spins, but I still preserve the single charges. So now what I'm doing is I'm choosing, of all the possible charge configurations, essentially what I'm choosing is sodium chloride, right? So it's like a salt. So I'm having the neighbors of each are going to be charges of opposite sign, right? So the way in which you can think of this pyrochlor lattice now along 111 is it's a stack of triangular lattices and Kagome planes. So we have one triangular plane, one Kagome plane, etc. Okay, so again, I project this into 2D, and we think, what are the possible excitations we can get? This seems a bit repetitive though, but it's not. So you see, I can also put this kind of line excitations even when I can't have any spin flip. But the difference here, and this is quite crucial, is that this is no longer a divergence-free constraint. So before I had to conserve charge, here I no longer need to conserve charge. And what that means, because I can flip any two spins in a single tetrahedron, what that means is that I can do now some excitations that were not allowed before, like I can start a line here, then turn back, go back in. I can also do this kind of loops. Those are allowed. So this is no longer your usual castelli transition. You already have excitations even at the high field side. You can always have a finite probability of putting these loops in. Right, you can even put transverse line. Right, so even some transverse line. So the way in which we can look for this transition is by looking at the parity of flip spins on each of these planes. So that would tell us whether there's a line that's really piercing through or if we're only seeing loops around. Right? So this is going to separate the two phases. Right, so what's the nature of this transition? So to look at what happened there, what's best to do is to consider the Kramers-Vanier duality of these. So you go from this, which lives in the pyrochlor lattice, to an Ising model that lives on the diamond lattice. So if you look at the center of each tetrahedron, they form a diamond lattice. And if you do the high T and the low T expansion of the partition function for each of these, you get that they're both identical. If you associate these tangents, you associate with that exponential. So essentially, if you associate your field in your system to your exchange constant in the Ising case, you get identical systems. So because you can see here that J is positive, so this transition corresponds to an Ising ferromagnetic transition, but now the high field phase corresponds to a low J paramagnet, right? So the high field phase on your spin liquid corresponds to the low J on your Ising Hamiltonian, and the low field corresponds to high J. Right, okay, so we did some loop Monte Carlo simulations on the system, and this is what you find. You find that the magnetization gives you this metamagnetic transition. The heat capacity shows you that there's a transition there. And once you want to scale them, this is for different system sizes, you see that they scale very nicely with Ising exponents. So, and the other thing is that when you look at the susceptibility, you see that the susceptibility also scales with the same exponent than the specific heat. And this is because of what we were saying before, right? The field in one system is associated with J in the other. So both field and temperature scale the same way. Right? So you have the same critical exponent for both. And if you now look at the parity, so your order parameter, you see that you have a nice transition there, and the order parameter also scales like an Ising type transition. There's an additional bit of information you can get from this Kramers-Vanier duality, because you know that correlation functions on the dual corresponds or are proportional to the free energy cost of defect on your system. So you see that now on the paramagnet, the correlation function decays exponentially. That means that the free energy grows linearly, so these are confined. These effects are confined. But in the ferromagnet, the correlation function tends to the magnetic order parameter, and that means that this is finite for any separation, and that means that you're deconfining these loops. So this is like a deconfinement transition. Okay, the last bit of information you can get from what we did is something in the lines of what Stephen Powell and John Joker did for the Castellane transition. So now you can think of these lines as if they were Ward lines of bosons, right? So instead of a 3D system, you have a 2D system. Your field direction is now time, and you can do a two-dimensional theory of that. So the difference here, as opposed to what we had in the Castellane transition, is that now the number of bosons is no longer conserved, because now you have these loops that can appear. So you can have pairs of bosons that disappear. So you need to add these additional terms that no longer conserve the boson number. And that means that now you have a Z, which is 1 instead of the Z2, which you had in the Castellane transition. So the question now is whether one can see this in real life. So the way, or the reason why we started thinking about these Hamiltonians is because we started considering what happens when you consider the magnetoelastic coupling in spin ice. So in spin ice, what you have is that the J is dependent, so it's a super exchange interaction is coming from the oxygen that sits on the center of this tetrahedra. So if you think of the Woodenough Kadamori Anderson picture, the idea is that if you now have a displacement of an oxygen, that will change your J's here and your J's there in opposite directions. So now if you consider your Hamiltonian, where you have elastic term, and now you have your exchange interaction that depends on the displacement of these oxygens. And if you expand this to first order and you integrate out the elastic term, you see that you get this additional term, this additional 4-spin term. So now if you're working on the limit where JML is much higher than J0, you find essentially one of these 4-spin Hamiltonians. So our idea is that we're trying to look for softer spin ices and see where we can get this type of monopole liquids on those systems. And okay, so if you don't believe what I said before, that if you integrate out, you get this Hamiltonian, the other thing we did was to do a full Monte Carlo simulation. So you do a Monte Carlo simulation where you allow both magnetic flips, but you also allow the system to move. Right, so you allow distortions of the oxygen, and this is what you get. So essentially you get one soft transition, like in spin ice, to a lower field state. And if you look at the density of molecules in that state, you see that it goes to 1 at very low temperatures, and it gives you an extremely nice paramagnet there. So this is a work in progress, but we hope that we'll eventually be able to add to this a bit of experiments. Okay, so let me move now to the dynamics. Okay, as I said before, one of the problems we always have is that even if you take really nice, really clean single crystals, you still get that the system freezes at low temperature. So below 800 milli-K, 700 milli-K, it's very difficult to work. And this plot here is a combination of work done by many people over the years, and there are small discrepancies, but you see that essentially we all coincide in that once you go below 1K, the system becomes really slow, and if you fit some Arrhenius law to the high temperature, you see that the system goes super Arrhenius at low temperatures. So below 500 milli-K, you're already talking to 1,000 seconds, and that's really long. And even if you go to... I'm going to show you one way in which we did. So that's the thing. So Matsushita, for example, did AC susceptibility. I'm going to show you how we measure this. So the one that says this work, that's the one I'm going to show you. So what we did was to measure noise. And so Dusad did noise, and the rest are all AC susceptibility. And some, I think, either Matsushita or Schneider also did magnetization, relaxation of the magnetization. That's why there's small discrepancies between them. Also, they are completely different crystals. Okay, so what we did here, it was in collaboration with PTB in Berlin, was to measure magnetic noise. So essentially, we took one of these samples, and they attached this squid to a sample, and then we put it in this magnetically shielded room, zero field, very low temperature, and then we just measure the magnetization as a function of time. This is your raw signal, magnetization as a function of time. This is, for example, 0.8 K. So this is what you're looking at is what's the magnetic noise that's coming from your excitations that are moving around. So to get an understanding of this, you can look at you can do the Fourier transform, and this is for different temperatures, but let me try to break that down. So essentially what you're getting is something that looks like this. You expect to, naively, what we expected was that it would fit to a Cole-Cole, so that the power spectral density would fit to a Cole-Cole, and that what we'll find was the exponent would be 2, which will be this random walk of these excitations. What we found was that we could extract tau. Tau matched very well with what other people were getting, but the exponent was not 2 at any of the temperatures we looked at. So even at high temperatures, and it looked like it was going up and would eventually reach 2, but once you got into the spin ice regime, so 1 Kelvin is about where you start becoming spin ice, and you see that it's even worse than before. So you ask, why is there one gap there? And that's because we're using a different frequency, sorry, a different sampling rate for high frequency than low frequency. So it's the same measurement, same sample, but there's where we switched. It's only because of space, right? So the number of, the amount of data you can store in one hard drive, it's limited, so we had to change that. Okay, so let's see at different temperatures what you get. So this is when you're at 0.8 Kelvin, you're at thermal equilibrium, you're getting a very nice fit to your Cole-Cole, and from that you extract tau and alpha. This is what you get where you're at very high temperatures. Again, you get a nice fit and you can extract alpha, but of course when you're out of equilibrium at very low temperatures, what you get is not, it depends on, so this curve will depend on the history, how you cool down, etc., and what you're getting is something that is not feasible. So we'll be concentrating on the regime. So in my computer and there's a difference between a color here and a color there, but you can't see it there. So we'll be working between 1K and 0.8, 0.7K, right? So that's the regime where it's spin ice and we're not out of equilibrium. Okay, so we try to understand why was this happening, and we thought, well, maybe this is coming from the fact that you have these dipolar interactions, and essentially your monopoles are no longer working on the flat surface, but you have this rough surface because of the interactions. But that gave us very small corrections to the exponent. So we went back. This is a work done by Tomasello, Castelnuovo, Mester, and Quintanilla, and what it turns out is that when you look at how one monopole moves from one side to the other, then we need to go back to spins. And you see that in 2/3 of the cases, so here you have this monopole, and that's the spin that's going to flip to move that monopole from one tetrahedron to the other. And if you do a calculation of what are the local fields at that spin, you see that in two cases, you have a transfer field and the other you don't. So essentially now what you get is this sort of bimodal distribution. In some cases, in 2/3 of the cases, there's a high chance of flipping, and in 1/3 of the cases, there's a very low chance of flipping. Right, so essentially what's happening, so now every time you flip from one side to the other, it's not true that you can choose any of these three. So before we knew that that was not necessarily true, because in some cases, if there's another monopole there, you can't move. But now we saw that it was even worse than that, that of the remaining spins, some will be in a state which is very slow to flip. So what we did was now, what we call this beyond standard model, is to model this by essentially calculating at each step, you calculate what's the local field at your site, and then you assign that a tau, either fast or slow. So we saw that so we started with the simplest case with the lowest number of parameters. We thought, okay, tau slow, we're going to say it's infinite. Those are non-flippable spins. And we only adjust tau fast. And that's what's shown here. So those are the experiments, and that's the standard model are the gray ones, the one that I was telling you that we were not able to fit to the data. And the black ones are the ones where you're using this beyond standard model with just one fitting parameter, which is tau fast. The other thing that this solves reasonably well, or very well, is this non-arrhythmious behavior at low temperatures. You see that once you start looking at what happens with relaxation time, the beyond standard model gives you a very nice explanation of what's happening there. So let's try to understand this a little bit better. So essentially what's happening here is that you're creating a sort of dynamical fractals. So the idea is that once you start moving, you are no longer allowed to explore the whole space, but you're dynamically constrained to look at only some sites. So what I'm plotting here is the number of sites you can access as a number of hops. And you see that in the standard model, essentially it goes to n cubed, so essentially exploring the whole volume, while once you put this dynamic constraint, you see that initially you're moving on something that goes like n to 1.85, and eventually, of course, you manage to once your times are long enough, you go back to n cubed. So what I'm saying is that it's not that you're creating a proper fractal structure, these are dynamical fractals, so it's a dynamical constraint on your walk. Right, so we can see it here more pictorially. This is, sorry. Yes. No, I didn't add quantum flux. Yes. Yes. It's the opposite, because essentially what we said is that the fluctuation we had were only valid for some sites and not for all. So before we were saying you have quantum fluctuation on all sites. Now we said it's only on some sites that you have them. So it's not that we added the transfers, it's we removed the transfer from one of them. Okay, we can discuss that because I'm not sure. No, okay, yes. So essentially because it's quantum fluctuations, but the moments are very big. Essentially, they happen less often than what they should. Yes. We can discuss. Sorry. Okay. Yes, exactly. Yes. That's the trick. Yes. We're saying fluctuations are classical because the moments are big, but the way in which they eventually happen. Okay, but as I say, we can discuss it at length. Okay, so now if you look at how pictorial how this goes, is that in the case where you were not limiting this, you're getting essentially you're covering volume, while when you have this dynamic constraint, you're getting a very sparse coverage of the system. You see that of all the, for example, in this case, you go up to 12. You had 2,071 sites that were available, but you will explore 130 of these. So even in the absence of any kind of disorder, you're getting a very low coverage or a very high tau. Okay, so I'm moving now to the last bit, which is, I hope this is not very disappointing. I'm going to show you like a teaser of what we have. This is very recent data, and it's not, we think that the best bit is not yet analyzed, so, but we think, I thought it would be nice to discuss it here so that if anyone wants to discuss it later with us, it would be very nice. So the question is, what happens if you do a quench? What's the dynamics after you do a quench in this system? And let me start here. So this is, suppose you measure the magnetization and you just do a Faraday force magnetometer. You have your sample there. You put a gradient of magnetic field, and you measure the force on your sample, and you put your sample on a floating plate, so you can measure the capacitance. And so if you measure capacitance, you can calculate your magnetization. So if you do that in the dispersion titrate, this is what you get. This is field now along 111, the same than before. This is temperature. So if you are, this is for spin ice. If you are at high temperatures, you get this rise to one plateau. Essentially what you're doing there is you start polarizing your spins, and what you do is you polarize first, you polarize all the spins that are on the triangular planes, and if you can do that without breaking the ice rules, so that gives you just a linear rise, and then you get a plateau. And then if the field is big enough, so of the order of 1 Tesla, you can eventually break the rules and polarize the whole system, and you get a conventional metamagnetic transition. But now you see that as you start lowering the temperature, you start getting these strange ridges there, that sort of different jumps. And we were not sure what was happening there. And when we started looking at this with more carefully, we saw that essentially this is what you were getting at, let's say, 250 milli-K as a function of field. This is with a magnetic sweep rate of 0.1 Tesla per minute. This is what happens now when you do half the rate. You see that the transitions moved, and if you do you have that again, you lose one of the transitions, you still get the other, and if you have that again and you have it again, you see that you get a very smooth curve. Now, usually you would say that the slower you move, the closer you should be to equilibrium, but here equilibrium will be starting from 0 and going linearly up there. So the slower we went, the further away we were from equilibrium. So it was sort of puzzling. So as I said, below there are no jumps. And of course, what I was plotting there is magnetization as a function of field, but that's the field you put in, not the field the sample sees. So once you correct for the demagnetization factor, so this is thin samples that look like that, magnetization factor of 0.01, you see that these jumps are really not phase transitions, they're non-equilibrium. You see that they move back, right? So that is telling you straight away that this is a non-equilibrium effect. So essentially it's a trigger effect. Once you started that, even though the field, the internal field is going down, the system is still jumping to where it should be. And you see that once you see that, the system is really moving towards equilibrium as in those cases. But again, it was closer to equilibrium when you were flipping faster. Okay, so the question is what's happening there? And again, we can use monopoles there. Essentially what's happening is that you have this mismatch between the dispersion relation of your magnons and your phonons. So essentially what's happening is that you start putting in field, you start having a Zeeman energy, but you have nowhere to dump it. So essentially you're collecting the Zeeman energy, but you cannot dump it. And eventually, you find a way to dump it. And once you dump it, you warm up your phonons. So essentially, what you have is this diffusive term here. You have the heat that you're creating from the monopoles coming from this Zeeman energy. And if you manage to balance these two, you can move smoothly. But if you don't, if the second term wins, then you start creating more monopoles. More means that the second term wins more. And essentially what you get is this sort of magnetic deflagration. So the energy dumping helps create more excitation, which dumps more energy, and you get this burst. Excellent. Okay, so one way in which you can check whether this is true or not is by directly measuring the temperature in the sample. So we attach a thermometer directly into the sample, and we measure simultaneously the magnetization and the temperature. So this is what you get. And then this is the power you will get from this Zeeman term, right? So the derivative dMdt times h is going to give you the power. So now you can calculate, from the magnetization you can calculate the derivative. This is the power you're generating, and this is the temperature of your sample. So the whole thing about this is that now if you measure the temperature of your sample as a function of field, see that you get these huge spikes when you have these, I don't know how to call them, either cascades or avalanches. Right, so, but the nice thing about this, and this is the whole point of bringing up today, is that this is a very nice way in which you can now do study on quenches, right? Because now you take your sample, you start moving your field fast, and then you move it fast back to zero. And essentially what you've done, if you created one of these spikes of temperature, but you're creating one of these spikes in the system itself. So you have the whole experimental setup is very cold, but you managed to introduce some heat in your spin system, which is exactly what you wanted. So that's why you can get these spikes, which are less than a minute, right? So let's say in less than 30 seconds, you get from, let's say, 500 milli-K to 100 milli-K. Right, so our idea was, and this is something that was based on our work, was already used by Paulsen and collaborators to study magnetization. But the question is, we thought, okay, so it would be nice, given that we have these complex dynamics, it would be nice if we can do this to neutron scattering. So do some diffuse scattering at low temperatures, induce a quench, and see how that signal decay. So the nice thing is that these new systems where you're using these spallation sources essentially are clever enough that they're giving you a timestamp for each neutron you get. So essentially now you can, even without bothering people at Oak Ridge, you can do a measurement without any additional constraint of what they would usually do, and you're getting a time-stamped neutrons. So essentially, we did our first experiment, and this is, as I said, this is preliminary data, and we would like to see more of that. But essentially, what I'm showing you here is we do one of these quenches, and now we are integrating some area of S of Q, and you're plotting that as a function of time. And that's telling you, so this is for 100 milli-K, and this is for 300 milli-K, and you can feed that, and you can get taus for different, you can get taus for the different peaks you're seeing in the diffuse scattering, right? So there's no order, as I said from the beginning, this is a liquid, there's no long-range order, but you still have short-range correlations. And now, with this trick, you're able to see, this is for different fields, you're allowed to see what's happening for these different modes, how these different short-range correlations are establishing at different times. So we're already seeing that we get different times depending of the different correlations. So we want to do a bit of a longer analysis of that and see whether we can do a proper characterization of what are the dynamical modes and how they behave. So okay, so that was all I wanted to tell you today. So essentially, I started with these topological transitions on the system. As we saw, one of the reasons why we couldn't do a really nice job on the topological transitions is because of the dynamics. But the dynamics itself, it's something interesting to look at. And it's intrinsic to the system. So it's not like spin glasses. It's not something that's coming from disorder of any sort. It's intrinsic to what it is. OK, so thank you for your attention. So according to that, I left 7 minutes.
Thank you. So we have plenty of time for questions. So maybe you can, oh.
You had two descriptions for the 1-1-1 field direction.
Yes.
One was in terms of the Ising field, the Ising mapping.
Yes.
And the other one was in terms of a Bose model in 2+1 dimensions with
Yes.
no conserved charges.
Yes.
What is the transition in the Bose language correspond to? The actual topological transition, what would it correspond to in the bosonic language?
It's this deconfinement transition.
You have a boson that has no charge conservation. What phase transition do you have in that model?
It's how do you call this? It's a hidden order. So it's it's a Z2 transition.
Okay.
It's a hidden order. So
what is hidden? I mean, just give us some more what do you mean by that statement?
I'm not sure I understand your question, but
you have a phase transition. You have two different, you have the original model, you have your Ising duality mapping.
Yeah, so in one, when you create these pairs, they're essentially confined. And in the other, you can move them. So let's say, these pairs you can create, these boson pairs you can create.
Yeah.
In one phase, they're confined. In the other,
I understand this in the duality model to the Ising model.
Yes, the same is true for the...
Okay. But the boson model, I claim I know everything about this model. And I don't see the transition that you're referring to. It's a 2+1 dimensional boson that is condensed. It has sound excitations, but what transition takes place in this model?
Well, what I would say is that it's a transition between having excitations that are either localized or delocalized.
Okay.
That's...
He doesn't have, he has sent the charges to infinity, so he only gets lines, right? It's line proliferation, basically.
No,
set the transition, no?
It's 2D.
Right, but you only get loops. One phase has no loops, and the other has finite density of lines, but it doesn't have point-like particles. So I don't think it fits into any sort of simple transition, but it's unstable once you add the energy to create charges, right?
Yes.
Yeah. Yeah, so that's then the transition rounds up.
I guess that the loops are the ones that are giving you, so once you can deconfine them, they are the ones that are giving you the charges.
So I was going to ask you about this part of the dynamics. You know, at what is the, for the actual material, what is the, you know, energy scale in temperature at which you start seeing, you know, the quantum aspect of the spin ice, like this, you know, for example, the energy associated with this ring exchange.
Yes.
So why shouldn't, you know, one include, because you went to 1 Kelvin, I think that's already quite low. So why are there not deviations from, you know, actual quantum behavior of the system?
So your question is, why is it that at 1K we don't see quantum effects, essentially?
Yeah, maybe one question is, what is the scale in the material?
So J is of the order of 1K. But this is an effective J, in the sense that if you look, you have an antiferromagnetic exchange, which is of the order of 2K, and then you have a dipolar interaction, which is of the order of 2K.
But does the energy for the ice violation is 1 Kelvin?
It's 1 Kelvin.
I see. So then the other energy is even much lower, probably.
Yes,
You're
it
still
is
okay.
much lower.
Okay, okay. Thanks.
Plenty of time. So maybe you can explain again that part that Jorg asked you about the why quantum fluctuations don't seem to kill the Arrhenius law, the activated behavior. You said it's big objects, but I couldn't understand
I was
the
saying
reasoning after that.
I was saying it's big moments too.
Yes.
So in that sense.
And the lines, I suppose, right? The big objects you're talking about are the moments?
No. I'm saying the moments are big. So it's
Okay.
10 Bohr magnetons. So that's already, if you want.
And how do the quantum fluctuations come in and help you? Because as he said, I mean, you're putting quantum fluctuations in a system, and you still have the Arrhenius law.
Yes. Well, let me start.
I understand the reasoning that you have a restriction on the phase space of the
Yes.
of the
So
lines, but
Let me start from the beginning.
okay.
So one thing to say is, if you do, if you want, we were doing the opposite. We were not putting in. We're restricting. So we're saying,
Right.
If what you have a transverse field that helps your transition, notice that you don't have it at every site. So it's not that we're saying that we have an Arrhenius. We're saying we don't have an Arrhenius. We're saying exactly the opposite.
Okay, I think, well, maybe.
Yep.
Okay. Well,
Yes.
How are you doing this quench? I didn't understand exactly the procedure during the experiment. Could you give me
Well, essentially, you cool down,
yeah.
and then you flip the, sorry, you sweep the field. So you cool down,
Yeah,
and now you flip the field from 0, let's say, to 0.1.
yes, and you measure the vortex structure during the sweeping,
No.
or not? Or,
So you feel the sweep there, and you get this spike, and then you flip fast down. And then you start looking at your signal.
okay. You sweep, shut down, and observe the system.
Yeah, so essentially
okay.
with the field, the only thing you want to do, you don't want to measure with field necessarily. The thing you want to do is you want to trigger one of these spikes. And once you warm up the system, you go down to zero
because
field.
times
let's say
were
you're-
shorter, so I didn't understand in what moment are you measuring, but no, I understood the point, yeah.
Okay, yeah,
Okay,
it's
okay.
not, what do you mean by shorter time? So these are minutes, you see? So essentially it takes you less than 1 minute to do the spike, and then we're measuring up to
Some hours.
1400
Okay,
moments. Yeah.
okay.
That's why we can also do the thing of measuring at finite fields, right? So you can do the flip, so you can do the sweep and trigger, and then you can go to some field and measure at that field. Again, that happens there, and then, and then you start measuring.
Okay, thank you.
Any more questions? Okay, if not, let's thank Santiago again.